Hello again, higher algebra students. Back again after a delicious bowl of Frosted Flakes to get me rolling. Here on the third lesson of Unit 2. This lesson is going to really focus on rational roots and exponents, and so we'll jump right into it here. And this again is a follow from Lesson 2. So as a reminder, we have the 5 main rules that we're going to still focus on. We have the product rule and the quotient rule, where we either add or subtract the exponents. Power to a power, which we'll use especially to try and get these bases to be equal. Zero power rule, so when you see that number 1, that's a reminder that something could be raised to the 0, really anything. And then the negative exponents, that reminder to be able to swap these from the denominator to the numerator based on that negative exponent. Got the power table, so don't forget that you have this resource as a way to be able to say, oh, 256 is, if I take the fourth root of that, I know that the fourth root of that is going to be 4. So some of those things that can be shortcuts for you to be able to look at a number and say, oh, 243, the fifth root of 243 is 3, since that's probably not something that you have at the tip of your tongue when you see the number 243. So use this power table to your advantage. Again, to solve these more complex exponential functions, you want to make sure you have that common base and that you have a single base, and so it's not 2 and a 4 and in one base, but rather just the 2 or just the 4. You're going to set these equal with these equal bases, and then solve, really solving those exponents as being equal. So here are some of the toughest things you would see here. When you look at a question like this one here. So again, we need to get these bases to be the same. And so hopefully one thing that's in your mind right now is that a base of 2 is really the goal here. Because 2 times 2 times 2 is 8, so we can say that this is 2 to the third to the negative x, okay? This one's already a 2, so that's just 2 to the 5x. And then again, this here would be 2 squared is the 4. So again, I'll just put that in parentheses because I'm really just replacing the 8 and the 4 with 2 to the third and 2 squared. And then I have to the 3x plus 1. Now I have all these bases the same. Now I'm going to just finish my power to a power rule here, since I now have a 3 and a negative x. So that's 2 to the negative 3x equals 2 to the 5x times, and now power to a power again. So this is 2 to the 6x plus 2, because it's really like distributing that 2, since power to a power again is multiplication. Again, x to the a to the b equals x to the a times b. So now I've got here a product rule scenario. So the product rule tells me that this is 2 to the negative 3x equals 2 to the 5x plus 6x plus 2. Again, the product rule here says you just add the exponents, so the 5x gets added to the 6x plus 2. Finally, we have the equal base, and we can now write it as negative 3x equals, I'm just going to combine these two, so I have 11x plus 2. Now I can either do this in 2 steps and move that negative 3x over and then move the 2 back, or I can just move this to negative 11x, move that over. So that gives me now, let's change our color here. That gives me negative 14x equals 2. And now I can divide both sides by negative 14. So I get x equals negative 2/14 or negative 1/7. So very involved question there. And again, you wouldn't by any means be able to look at the original question and say, oh, that's negative 1/7 for x. But when you go through the steps, you can get that solved out. Another one here. So here we have to look at, again, what's our common base? 8 would be nice, but 8 does not work here because it's 8 times 2, not 8 squared, that gets 16. So we can't use 8. 4, can we use 4? Let's see, 4 times 4 is 16, times 4 is 64, and 4 times 4 is 16. So 4 does work. So let's think about this now. what would replace 1/64th? Well, that would be 4 to the negative, because it's got to be in the denominator, and 4 times 4 is 16, times 4 is 64, so this is 4 to the negative third to the x minus 1. And then this side would be 4 squared to the x plus 3. Now, power to a power gives us 4 to the negative 3x, and now negative 3 times negative 1 is actually a positive 3, equals, and again, it's like distributing this power to a power. It's 2 times x plus 3, so that's 2x plus 6. Now, just like that, we're now in an equal base situation here. So we have negative 3x plus 3 equals 2x plus 6. Now this becomes a little nicer for us. This is a review of last unit now. I'm going to take that smaller x and move it over, so I have 3 equals 5x plus 6. Subtract the 6 from both sides, and that gives me a negative 3 equals 5x. 6 is gone there, so 3 minus 6 gave us the negative 3. We now divide by the 5, so we have x equals negative 3/5. Again, you wouldn't look at that original question and say, oh, that's negative 3/5. So got to go through the process there. Here, this one's going to be a little quicker because we have a 25 and a 5. So we can see pretty quickly here, hopefully, that 25 can be rewritten as 5 squared. And again, it's to the x plus 3 equals 5 to the 5x minus 9. That one's as is. We do need to take that power to a power here, so that's 5 to the 2x plus 6 equals 5 to the 5x minus 9. Okay, so we distribute out that 2. So now we've got those equal bases. So we've got 2x plus 6 equals 5x minus 9. Go to the smaller x and move it over. 6 equals 3x minus 9. Okay. And then I'm going to add the 9 to both sides. Again, this is now a recap of last unit. So 15 equals 3x. And finally, I can divide by the 3 on both sides. So x ends up equaling 5. And again, if I put the 5 in there, that would be 5 squared to the 5 plus 3. So that would be 5 to the 16. And then if I put 5 in for the other one, 5 times 5 is 25. 25 minus 9 is 16. So quick check there. Yes, they do both end up being an exponent of 16 if you put 5 back in for x. Fourth and final one here. Okay, so we have, first of all, something to the 1. It looks like 7 is going to be our convenient base here. So I'm just going to rewrite this as 7 to the 0. Okay, again, if something equals 1, then we just raise it to the 0, and we just have to figure out what base we want. And then here we have a product rule. So this is 7 to the 4x plus 5. Set the exponents equal to each other. 4x plus 5 equals 0. Subtract the 5. Negative 5 equals 4x. Divide by 4 on both sides. So x equals negative 5/4. Okay, so pretty involved there, but again, it's all a process that you can work through consistently. And if you don't get those common bases, it's not going to work out. So it's kind of a checks and balances right in there for you. So just a reminder that when we get to fractional exponents here, that root x is the same as x to the 1/2. Cube root is the same as x to the 1/3. Fourth root is the same as x to the 1/4. So you're going to see more and more of that. So just a reminder to be able to take those and convert them to fractions. And again, if you do the root first before squaring or cubing or raising to the 4th or anything, you're going to work with nicer numbers. So it's always good to do the root values first. So if I have the x cubed with the 4th root, again, now the cube is there and the 4th root is the denominator. So that would just be x to the 3/4. And again, I could write this as x to the 1/4 cubed. So keep that in mind. This will be helpful moving forward. This one here is just x to the 7 over 2 because you've got raised to the 7th, and then you've just got a square root here. So again, keep in mind that this is also x to the 1/2 to the 7th. Okay, if I just pull out the fractional exponent with a 1 in the numerator first, again, that can make your life a little easier down the road. This would be x, the 4 is the 4th power, but then there is the 5th root, so that's 4/5. And again, this would be x to the 1/5 raised to the 4th for future reference. And finally here, this is 1 over x to the 2/3, right? The 2 is the exponent and 3 is the root. And so because this is in the denominator, this would be x to the negative 2/3. So in this case, you could write it as x to the 1/3 to the negative 2 or x to the negative 1/3 squared. Either way would get you there because that power to a power would end up being 1/3 times negative 2, or negative 1/3 times 2 is going to always be negative 2/3. And so you could go either way there, but that would, again, be something that makes your life a little easier down the road. So rational exponents are just the idea that we have a fractional power. So this is a rational exponent is the idea of being 2/3. When we write this in a little more common method here, that would look like this. So again, that's 8 squared is cube rooted, which again is 8 to the 2/3, which based on how I was writing before could be 8 to the 1/3 squared. Okay, so 8 to the 1/3. So what's the cube root of 8? Well, 2 times 2 times 2 is 8. So the cube root of 8 is 2. So this is just 2 squared. Okay, so again, that would be that process of trying to clean that up. And again, if you square it first, that's fine. If you did 8 squared to the 1/3, that would be okay. But that's 64 to the 1/3. It's just a little bigger numbers that you're going to be working with. It will still end up with the same answer. Okay, so looking at this one, 27 to the 4/3, I would recommend saying that you answer this like this: 27 to the 1/3. So what's the cube root of 27? Again, this might be written like this as well. 27 to the 1/3 is 3. So this is just 3 to the 4th. So 3 times 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. 4 to the 5 halves, again, this would be 4 to the 1/2 raised to the 5th. It would look like this. You don't need to put the 2 in there because square root is just implied. Sorry, that's not neat at all. I'll write it again. So the square root of 4 to the 5th. Square root of 4, again, we can do that first if we want to, or we could do it last. But the square root of 4 is 2. I'm going to do it first because I'd rather work with that rather than taking 4 to the 5th and then square rooting that. That's just a little more work. And it involves bigger numbers. So 2 to the 5th, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. I might have said 18 there, 16. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Last slide here. Evaluating these without a calculator. I won't run through all of these right now, but this again would be 16 to the 1/2 raised to the 3rd. So that's 4 to the 3rd. 9 to the negative 1/2. So this is again 1 over 9 to the 1/2, which is 1 over the square root of 9. And so 1 over root 9 is just 1/3. Okay, 125 to the 2/3. Again, I would go 125 to the 1/3 and then square it. Okay, and the cube root of 125 is 5, so that's just 5 squared. Again, you can set that equal to 25. 81 to the 1/4 raised to the 5th. So 81 to the 1/4 is, let's see, 3 times 3 is 9, times 3 is 27, times 3 is 81. So that would be 3 to the 5th. And you can solve that out. 3 times 3 times 3 times 3 times 3. 4 to the 7 halves would be 4 to the 1 half, which is just 2 raised to the 7th. So this is 2 to the 7th. Again, you can keep multiplying 2 by itself 7 times. 625 to the negative 3/4. So this would be 1 over 625 to the 3/4. So I would write this as 625 to the 1/4 cubed. 625 to the 1/4. So this is where having that chart would be helpful to remind you that 625 to the 1/4 is 5. I actually forgot that off the top of my head as well. So, but 5 times 5 is 25, times 5 is 125, times 5 is 625. So that's actually 1 over 5 to the third. So this is 1 over 125. Wow, one like this here. 243 to the 2/3 to the 3/5. So keep in mind, power to a power means you multiply. So this is 243, and it's top times top, bottom times bottom. So this ends up being 243 to the 6 over 15. Oh, well, I'm not going to take the 15th root of something. That seems like it's extraordinarily difficult here. So what I'm going to do is reduce that fraction first. So this is the same as 243 to the 2/5. So this is 243, oh, didn't mean to write that, to the 1/5 squared. Well, 243 to the 1/5, this is again why that chart would be helpful. That is 3, so it's 3 squared. And finally, we've got this negative 64 to the 1/3. Now keep in mind, because it's a cube root, the negative actually can stick around. Let's see, the cube root of 64 would be 4. So this cube root of negative 64 would be a negative 4. Now, the reason this works, negative 4 times negative 4 times negative 4 does give you an answer of negative 64. Okay, whereas a negative times a negative is going to be always a positive value. So if I put into my calculator the square root of negative 64, that wouldn't work. So negative 64 to the 1/2, or the square root of negative 64, those would not work. But with a negative and a cube root, you can do that, because a negative times a negative times a negative is in fact a negative. So just a heads up on that. I'll leave it at that. Thank you for listening. Thank you for watching. As always, if you have any questions, please ask. We'll see you soon.